Okay, everyone, welcome. Let's dive straight in today. We're looking at something called PRIMA.
That's right, the Probe Far Infrared Mission for Astrophysics.
And the big idea here seems to be unlocking some really fundamental secrets about cosmic evolution, things hidden in the far infrared light.
Exactly. You know, we've got amazing eyes in the sky like JWST looking at infrared, ALMA at millimeter waves.
Right.
But there's this really crucial window, roughly 25 to 300 microns, where just the huge amount of energy pours out from, say, really intense star formation or growing black holes.
Okay.
And PRIMA, it's specifically built to see right into that gap.
So bridging a gap, seeing a part of the story we sort of missed, what makes PRIMA the tool for this job then, and what big questions can we finally ask?
Well, the simple answer is sensitivity, just unprecedented sensitivity.
Okay.
To catch these really faint signals, PRIMA uses a 2-liter telescope, but here's the thing, it's cooled way down, like 4.5 Kelvin.
Wow, that's incredibly cold.
It is, and the detectors inside, even colder, less than 1 Kelvin.
Okay, why so cold?
That extreme cold is the key. It lets them achieve what's called photon-limited sensitivity.
Photon-limited. What does that mean in practice, like for the science?
It means they can basically count individual photons, particles of light. They're capturing almost every single bit of information the universe sends their way in that band.
Right.
Compared to what we had before in this range,
Yeah.
we're talking potentially 1,000,000 times more sensitive at some wavelengths.
1,000,000.
Yeah, it's not just a bigger number, it completely changes the game. It means getting a full spectrum, like a chemical fingerprint, of something maybe in an hour.
An hour. Compared to what?
Compared to maybe needing a whole week just for one object before. So you go from studying, I don't know, a handful of things, to potentially thousands, building a whole library of cosmic history, not just reading like one page.
Wow, okay, 1,000,000 times better.
Yeah.
It's like giving astronomers infrared superpowers. So what cosmic puzzles does this let us finally get a handle on?
Really fundamental stuff. Origins, like when did the universe first start getting, well, dusty and metallic?
Ah, the first stuff.
Exactly. PRIMA can measure the amount and even the type of dust way back across cosmic time. It shows us when those first solid grains, the things that eventually build planets, even complex organic hydrocarbons, when they first showed up.
And it sees through the dust too, right?
Precisely. So it gives us a clearer view of heavy elements, one that isn't biased because the dust is blocking the view like it does for visible light.
So tracing the ingredients back to the start, how does that connect up to, like, whole galaxies?
It's all connected. PRIMA can literally map gas flowing, the raw fuel flowing into galaxies, moving through them, and even getting blown out.
How does it map that?
By tracking specific spectral lines in the far infrared, things like ionized carbon, C to I, or hydroxyl, OH. These lines don't just say gas is here, they tell you about the conditions, the temperature, the density, and crucially, the movement.
So are galaxies fueling up to make stars, or are they, like, burping stuff out because of black holes?
Both. And speaking of black holes, PRIMA can directly measure how fast the supermassive ones in galactic centers are actually growing, especially the ones hidden deep inside dusty systems.
Huh. So the dust grains, they're building blocks for planets, but they're also mixed up in feeding black holes. Didn't really think of that connection.
It's a whole cosmic cycle.
Yeah.
And bringing it closer to home, this insight feeds directly into understanding how stars and planets actually form.
You mean like in those dusty disks around young stars, protoplanetary disks?
Exactly. Those, PRIMA will survey those, and debris disks too. It can measure the total gas mass accurately using a special molecule, HD hydrogen deuteride.
Why HD? Not just regular hydrogen.
Well, regular hydrogen H2 is super abundant, but actually really hard to see directly when it's cold, like in those disks. HD is much rarer, but it lights up nicely in the far infrared and acts as a really good tracer for the total gas available to build planets.
Got it. A proxy.
Right. And it can trace water, too, both water vapor and ice, which is, fundamental for figuring out how planets form and how water gets delivered to potentially habitable worlds.
And magnetic fields, I thought those were invisible.
They mostly are. But PRIMA uses polarimetry, measuring how light is oriented, and that can reveal the structure of the magnetic fields guiding all this gas and dust, affecting how stars and planets take shape.
That is just an incredible scientific range, all from this big leap in seeing far infrared light.
It really is. And a key part is, it's designed for everyone. Over 70% of the mission time is set aside for guest observers.
So the whole astronomy community gets to play.
Yeah, which guarantees a huge potential for discovery, finding things we aren't even looking for right now. Sometimes those are the most exciting bits.
Okay, so PRIMA feels like, yeah, the essential next step, bringing together this unique sensitivity, the wavelength coverage, the tech.
And opening up this vast discovery space for astronomers everywhere.
It makes you think, though, if it can peer right back to the origins of things like the very first dust grains, those hydrocarbons, the water-informing planetary systems, what kinds of unexpected connections might we find? You know, how does the stuff building planets deep down relate back to how black holes get fed or how whole galaxies evolved billions of years ago? That's something to really chew on.